There is a boundary in space where the laws of physics as we understand them cease to function. Cross this threshold, and time itself stops. Light cannot escape. Information vanishes. Reality tears apart. In April 2019, humanity photographed this boundary for the first time. A glowing ring of doomed light surrounding absolute darkness at the heart of galaxy M87 star. The image showed us something we'd only theorized about for a century: the event horizon of a supermassive black hole. But here's what keeps astrophysicists awake at night. That photograph revealed something we didn't expect. The shadow was larger than it should be. The light was structured in ways that challenge our understanding of gravity itself. And deep within those observations lies evidence of physics so extreme, so fundamentally strange, that it threatens to unravel everything we think we know about the fabric of reality. What happens at the edge of a black hole isn't just an astronomical curiosity. It's a window into the deepest mysteries of existence, where quantum mechanics collides with gravity, where time becomes space, where the universe might be destroying information that should be eternal. Today, we journey through evidence that challenges everything we thought we understood about the cosmos. Pice, prepare yourselves. We begin. In 1915, just weeks after Albert Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild did something extraordinary. While serving on the Russian front during World War I, battling a disease that would soon kill him, Schwarzschild solved Einstein's field equations exactly. The solution described something that seemed impossible, a mathematical singularity where matter collapsed to infinite density, surrounded by a sphere from which nothing could escape. Einstein himself rejected the idea as a mathematical abstraction, not something that could actually exist in the universe. But the equations didn't lie. Schwarzschild calculated a radius, now called the Schwarzschild radius, that depends only on mass. Compress any object below this radius, and it would create a region where escape velocity exceeds the speed of light. For an object with Earth's mass, that radius is 9 millimeters. For the Sun, less than 3 kilometers. The mathematics was elegant, terrifying, and seemingly fictional. For decades, physicists treated black holes as mathematical curiosities. Real stars, they believed, could never collapse completely. Some force, electron degeneracy pressure, neutron degeneracy pressure, something would halt the collapse before reaching the point of no return. In 1915, just weeks after Albert Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild did something extraordinary. While serving on the Russian front during World War I, battling a disease that would soon kill him, Schwarzschild solved Einstein's field equations exactly. The solution described something that seemed impossible, a mathematical singularity where matter collapsed to infinite density, surrounded by a sphere from which nothing could escape. Einstein himself rejected the idea as a mathematical abstraction, not something that could actually exist in the universe. But the equations didn't lie. Schwarzschild calculated a radius, now called the Schwarzschild radius, that depends only on mass. Compress any object below this radius, and it would create a region where escape velocity exceeds the speed of light. For an object with Earth's mass, that radius is 9 millimeters. For the Sun, less than 3 kilometers. The mathematics was elegant, terrifying, and seemingly fictional. For decades, physicists treated black holes as mathematical curiosities. Real stars, they believed, could never collapse completely. Some force, electron degeneracy pressure, neutron degeneracy pressure, something would halt the collapse before reaching the point of no return.
Over the following decades, astronomers found black holes everywhere. Stellar mass black holes like Cygnus X1, each one the corpse of a massive star, intermediate mass black holes in dense star clusters, and something far more disturbing, supermassive black holes lurking at the centers of nearly every large galaxy, each one containing millions or billions of solar masses. The black hole at the center of our own Milky Way, Sagittarius A star, contains 4 million times the Sun's mass compressed into a region smaller than Mercury's orbit. Yet somehow, despite this monster at our galactic center, stars orbited in stable patterns that allow astronomers to map the invisible giant through the choreography of visible stars. But the discovery of ubiquitous black holes raised profound questions. How do supermassive black holes form? Some existed less than 1 billion years after the Big Bang, not enough time for them to grow through conventional stellar collapse and feeding. Where'd they come from? More troubling, what actually happens at the event horizon? Einstein's equations predict infinite curvature at the center, a singularity where density becomes infinite and our equations produce meaningless infinities. Physics, as we know it, fails completely. And the most disturbing question of all emerged from theoretical physics. What happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed, but black holes seem to erase it permanently. This conflict, the black hole information paradox, threatens the logical consistency of physics itself. But this represents just one piece of a much larger puzzle hidden in the shadows of space-time.
On April 10, 2019, the Event Horizon Telescope collaboration unveiled the first direct image of a black hole's event horizon. 8 radio telescopes spanning the globe had worked in synchrony, creating a virtual telescope the size of Earth itself. Their target, the supermassive black hole at the center of galaxy M87, some 55 million light-years away. The image showed a ring of orange light, photons from the accretion disk, bent and amplified by the black hole's gravity, surrounding a dark central shadow. That shadow measures about 42 micro-arc-seconds across as seen from Earth. To put that in perspective, it's like photographing an orange on the moon. But here's where it gets strange. The shadow was approximately 20% larger than predictions based on the black hole's estimated mass. The asymmetry in brightness around the ring, one side glowing more brilliantly than the other, matched predictions from general relativity for a rotating black hole, but the specific pattern revealed the black hole was spinning at nearly half the speed of light. Scientists discovered something else in those measurements. The event horizon exhibited exactly the properties Einstein's equations predicted down to the resolution limits of our observations. No deviations, no unexpected structures. The most extreme gravitational field in the observable universe matched century-old mathematics with unsettling precision. In the 1990s, astronomers observing X-ray emissions from black hole accretion disks noticed something peculiar. The X-ray signatures showed iron atoms in the disk emitting photons at specific frequencies, but those frequencies were stretched, redshifted by the black hole's gravity. The most extreme observations came from stellar mass black holes in binary systems. Material in the innermost regions of the accretion disk, just 3 times the Schwarzschild radius from the event horizon, showed iron emission lines stretched by factors of 2 or more. These atoms were experiencing time dilation so severe that their clocks ran at half the rate of ours. Consider what this means. An observer hovering just above the event horizon would watch the universe outside speed up. Stars would be born and die in what seemed like moments. Galaxies would evolve and transform while subjective hours passed. The future would unfold at an accelerated pace. But for us, watching from outside, we would see that observers' time slow to a crawl. Signals from just above the event horizon would take longer and longer to reach us, redshifted to lower and lower energies, until the observer appeared to freeze at the boundary, asymptotically approaching the horizon, but never quite crossing it from our perspective. This isn't just an optical illusion. Time genuinely flows at different rates depending on gravitational field strength.
The event horizon represents the ultimate limit, the point where, from an outside perspective, time stops completely.
Perhaps the most spectacular evidence of black hole physics comes from relativistic jets, focused streams of particles and radiation that blast away from some supermassive black holes at speeds approaching that of light itself. The jet from M87's black hole extends for 5,000 light-years, visible in radio wavelengths as a coherent beam of energy punching through intergalactic space. The energy required to generate this jet is staggering, equivalent to millions of supernovae occurring simultaneously, sustained for millions of years. Scientists discovered the mechanism in the 1970s. The black hole's spin drags space-time around with it, an effect called frame dragging. Magnetic field lines threading through the accretion disk get twisted by this rotating spacetime, creating a kind of cosmic particle accelerator. Particles trapped in these twisted fields get flung outward along the black hole's rotation axis at relativistic speeds. But here's the remarkable part. The energy powering these jets doesn't come from the matter falling in. It comes from the black hole's rotational energy itself, a mechanism predicted by Roger Penrose in 1969 called the Penrose process. The black hole is literally slowing its spin by converting rotational energy into the kinetic energy of escaping particles. Recent observations by the Chandra X-ray Observatory and the Very Large Array revealed something stunning. The jets show regular oscillations, wobbling like a spinning top. This precession occurs because the black hole's rotation axis is misaligned with the accretion disk. The jet's wobble maps the black hole's spin axis with precision, revealing rotation rates and orientations that tell us how these monsters formed and evolved. But this represents just one piece of a much larger puzzle hidden in the quantum realm.
In 1974, Stephen Hawking made a calculation that shocked the physics community. He combined quantum mechanics with general relativity near the event horizon and discovered something impossible. Black holes aren't entirely black. They emit radiation. The mechanism is subtle. Quantum fluctuations constantly create particle-antiparticle pairs throughout empty space. These virtual particles normally annihilate each other almost instantly, but near the event horizon, something remarkable happens. If a particle pair forms right at the boundary, one particle can fall into the black hole while the other escapes. To an outside observer, the black hole appears to emit radiation. This Hawking radiation has a temperature inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is 60 nanokelvins, far colder than the cosmic microwave background. Such a black hole absorbs more energy than it radiates. But a black hole with the mass of a mountain would glow at room temperature. A black hole the mass of an asteroid would explode like a nuclear weapon. The implications are staggering. Black holes evaporate. Given enough time, far longer than the current age of the universe, even supermassive black holes will radiate away completely, leaving behind only faint photons scattered across an empty cosmos. But this raised a profound problem that Hawking himself identified. The radiation appears to be purely thermal, completely random, carrying no information about what fell into the black hole. If a black hole evaporates completely, what happens to the information encoded in everything that crossed the event horizon? That information cannot simply vanish. Quantum mechanics forbids it. Yet, the mathematics suggested it does. This conflict, the black hole information paradox, has tormented physicists for 50 years. It represents a fundamental inconsistency between quantum mechanics and general relativity, two theories that work perfectly in their own domains, but cannot both be correct at the event horizon.
In 2015, the Laser Interferometer Gravitational Wave Observatory detected ripples in spacetime itself, gravitational waves generated by two colliding black holes. The signal, designated GW150914, matched predictions from general relativity with extraordinary precision. Two black holes,
36 and 29 solar masses respectively, had spiraled together and merged, releasing 3 solar masses worth of energy as gravitational waves in a fraction of a second. But some physicists noticed something peculiar in the data. After the main signal, the chirp of the merger and the ring down as the final black hole settled into stability, there appeared to be faint, additional oscillations. These echoes arrived at regular intervals, as if the gravitational waves had bounced off something near the event horizon and escaped in pulses. According to general relativity's standard predictions, such echoes shouldn't exist. The event horizon is a perfectly absorbing boundary. Waves falling in don't bounce back. But some quantum theories of gravity predict the event horizon might have structure, a quantum atmosphere or firewall at the boundary that could partially reflect gravitational waves. Subsequent analyses have been controversial. Some research groups claim to detect these echoes in multiple black hole merger events. Others argue the signals are statistical artifacts, patterns in noise that look meaningful but aren't. The debate continues, but if the echoes are real, they would represent the first direct evidence of quantum effects at the event horizon, the place where quantum mechanics and gravity collide most dramatically.
The most disturbing theoretical prediction about event horizons emerged from calculations by physicists studying the information paradox. In 2012, researchers at the University of California, Santa Barbara proposed something radical. What if the event horizon isn't smooth and empty as general relativity suggests? What if quantum effects create a firewall at the boundary, a region of such intense energy that anything crossing it would be instantly incinerated? The argument goes like this. If information must be preserved, then the quantum state of Hawking radiation must be entangled with the information still inside the black hole. But quantum mechanics forbids a particle from being maximally entangled with two different systems simultaneously. Something has to give. The firewall hypothesis suggests that maintaining information conservation requires breaking the smooth structure of space-time at the horizon, replacing it with a barrier of extreme energy. This idea challenged general relativity's equivalence principle, the foundation of Einstein's theory, which states that freely falling observers shouldn't notice anything special when crossing the event horizon. The firewall would very much be noticeable. It would destroy anything that encountered it. Other physicists proposed alternatives. Perhaps information escapes through subtle correlations in the Hawking radiation, or perhaps black holes are connected to new universes through their singularities, or perhaps our understanding of space-time itself must be revised at the quantum level. The most remarkable discovery involves recent calculations suggesting that black holes might be vast quantum computers encoding information about everything that ever fell in across the microscopic structure of their event horizons. Every particle, every photon that crosses the boundary might leave an imprint, a holographic record of its quantum state distributed across the horizon's surface. The evidence extends beyond astronomical observations into the realm of fundamental physics, and it suggests that reality itself works differently than we imagined.
In 1993, physicist Gerard 't Hooft proposed something extraordinary based on studying black hole thermodynamics. He suggested that the information content of any volume of space can be encoded on its boundary, like a hologram. This idea, refined by Leonard Susskind, became known as the holographic principle. Black holes provided the key insight. Jacob Bekenstein had calculated in the 1970s that a black hole's entropy, a measure of information content, is proportional to the area of its event horizon, not its volume. This seems strange. Most systems have entropy proportional to volume. But black holes are different. Their information capacity scales with surface area. This forces us to reconsider fundamental assumptions about three-dimensional space. Any region is determined by the area of its boundary, then perhaps the three-dimensional universe we experience is actually a projection, a holographic image of information encoded on a two-dimensional surface.
String theorists at Princeton extended this idea, proposing that our entire universe might be a hologram projected from its cosmological boundary. Black hole event horizons became models for understanding this deeper reality. The information that appears lost when matter crosses the horizon might actually be encoded in the microscopic quantum structure of the boundary itself. Leading physicists like Juan Maldacena at the Institute for Advanced Study developed mathematical frameworks showing how gravity in three-dimensional space can be exactly equivalent to quantum field theory on a two-dimensional boundary. Black holes became laboratories for testing these ideas, the only place in nature where the connection between gravity and quantum mechanics becomes unavoidable.
At the center of every black hole, Einstein's equations predict a singularity, a point where space-time curvature becomes infinite, where density becomes infinite, where our mathematics produces meaningless results. This represents physics breaking down completely. Roger Penrose proved in the 1960s that singularities are inevitable inside black holes. Once an event horizon forms, he showed mathematically, nothing can prevent the complete gravitational collapse of all matter within it. The singularity isn't something that might happen, it must happen according to general relativity. But what kind of singularity? For a 9-rotating black hole, the singularity is a point, zero-dimensional, infinitely dense. For a rotating black hole, which all real black holes are, the singularity becomes a ring, a circle of infinite density within the event horizon. The mathematics suggests that you could, in principle, pass through this ring without hitting the singularity itself. Where would you go? The equations permit bizarre solutions. Passing through a rotating black hole's ring singularity might connect to a white hole, a time-reversed black hole that ejects matter rather than absorbing it, or to another universe entirely, or to a different region of our own universe, creating a wormhole through space-time. Physicists believe these exotic solutions are mathematical artifacts. Real black holes probably don't contain traversable wormholes to other universes. Quantum effects near the singularity, currently beyond our ability to calculate, likely change the picture dramatically. But we don't know. The physics of singularities remains one of the deepest unsolved problems in theoretical physics. Kip Thorne at Caltech has argued that nature abhors naked singularities, singularities not hidden behind event horizons. The cosmic censorship hypothesis suggests that singularities always form enclosed by event horizons, preventing them from affecting the outside universe. But some exotic scenarios, colliding black holes, rapidly spinning black holes, or quantum effects, might violate cosmic censorship. Recent computer simulations have found rare conditions where naked singularities might briefly form, visible to the outside universe. What happens if you could observe a naked singularity directly? Nobody knows. It would be a region where causality itself breaks down, where effects could precede causes, where the normal rules of physics cease to operate. Some theorists suggest naked singularities are cosmic censorship's ultimate safeguard. Nature renders them invisible by making it impossible for signals from them to escape coherently.
The Event Horizon Telescope continues to refine its observations. In 2022, the collaboration released an image of Sagittarius A star, the supermassive black hole at our galaxy's center. This black hole proved far more challenging to image than M87's. Matter orbits Sagittarius A star in just minutes rather than weeks, meaning the accretion disk changes appearance faster than the observation time required to capture an image. But those rapid changes contain information. By observing how the accretion disk flickers and evolves, astronomers can test predictions about turbulence, magnetic fields, and matter flow near the event horizon. Upcoming observations aim to capture video of the black hole's immediate environment, watching matter spiral inward toward its doom in real time. New radio telescopes joining the array will improve resolution further. The eventual addition of space-based radio telescopes could extend the baseline beyond Earth's diameter, potentially resolving structure at the photon sphere, the innermost stable orbit for light around a black hole, where photons circle the event horizon in perpetual orbits before eventually escaping or falling in. Recent breakthroughs suggest even more powerful probes. The Laser Interferometer Space Antenna, planned for launch in the 2030s, will detect gravitational waves from merging supermassive black holes billions of light-years away. These waves will encode precise information about the black hole's masses, spins, and the warped spacetime around them during merger. Each new observation tests general relativity in increasingly extreme conditions. So far, Einstein's century-old theory passes every test. But physicists expect that eventually, at small enough scales or extreme enough conditions, deviations will appear. Signals of quantum gravity, the theory that must ultimately replace general relativity at the event horizon.
In 2016, Stephen Hawking proposed a potential resolution to the information paradox. He suggested that information isn't stored inside the black hole at all, but rather in soft hair, low-energy quantum fields at the event horizon that record the quantum state of infalling matter. Other physicists pursued different approaches. Researchers at the California Institute of Technology calculated that Hawking radiation might be more complex than originally thought. Subtle quantum correlations between early and late radiation could encode information about everything that fell in. The information emerges gradually, scrambled almost beyond recognition, but technically preserved. The most radical proposal suggests we need to revise our concept of space-time itself at the quantum level. If space-time is emergent, constructed from more fundamental quantum information, then the smooth event horizon of general relativity might be an approximation that breaks down when examined microscopically. At the Planck scale, 10 to the minus 35 meters, spacetime might be granular, foamy, fundamentally quantum. String theory offers another perspective. In string theory's framework, black holes are collections of fundamental strings wrapped and vibrating in specific patterns. The information in any object falling into the black hole gets encoded in changes to how these strings are configured. Nothing is truly lost, it's transformed into the black hole's internal quantum state. These competing theories make different predictions about subtle effects, the exact spectrum of Hawking radiation, the gravitational wave echoes from black hole mergers, the microscopic structure of event horizons. Future observations might distinguish between them, revealing which path toward quantum gravity is correct.
Some physicists speculate about civilizations advanced enough to exploit black hole physics. A sufficiently advanced civilization could use the Penrose process to extract energy from a rotating black hole, dropping material into the ergosphere, the region outside the event horizon where space-time is dragged around by the black hole's spin, and recovering more energy than you put in by carefully choreographed trajectories. The maximum efficiency of this extraction is staggering. Up to 29% of the black hole's rest mass could theoretically be converted to useful energy for a maximally spinning black hole. This far exceeds nuclear fusion, which converts less than 1% of rest mass to energy. A civilization could power itself for billions of years by carefully feeding a supermassive black hole and harvesting the energy from its spin. Freeman Dyson proposed that advanced civilizations might build structures around black holes, black hole engines that would be detectable as unusual infrared sources, warm objects where no star exists. SETI researchers have suggested looking for such signatures as evidence of Kardashev Type II civilizations, those capable of harnessing the energy output of their entire galaxy. Even more speculative, if traversable wormholes can exist, a possibility suggested by certain solutions to Einstein's equations involving exotic matter with negative energy density, black holes might become gateways rather than dead ends. Civilizations capable of stabilizing wormholes could use them for faster-than-light travel through space-time shortcuts. These remain theoretical curiosities. No evidence suggests such engineering is possible with known physics. But black holes represent the most energy-dense objects in the universe. Any civilization seeking to master energy at cosmic scales would have to grapple with them. The most profound implications emerge when we consider what black holes reveal about reality's deepest structure.
Black holes force us to confront the question, what is space-time? In our everyday experience, space and time seem fundamental, the stage on which events unfold. But general relativity revealed they're dynamic, flexible, curved by mass and energy. Black holes take this to the extreme. At the event horizon, something remarkable happens to the concepts of space and time. The mathematical roles of space and time actually swap. Inside the horizon, the radial direction toward the singularity becomes time-like rather than space-like. Moving toward the singularity isn't a choice, it's as inevitable as moving forward in time. The future points inward. This suggests space-time isn't fundamental at all. Physicists studying quantum gravity increasingly believe that space and time emerge from something more basic: quantum information, entanglement networks, geometric structures we don't yet understand. Black holes, with their holographic encoding of information and their violent mixing of quantum mechanics and gravity, offer clues to this deeper reality. If space-time is emergent, then asking what happens at the singularity is like asking what happens when you zoom into a digital photograph until you see individual pixels. The singularity might not be a physical place at all, but rather a signpost showing where our description breaks down, where the emergent structure of space-time loses coherence.
Some solutions to Einstein's equations suggest that the interior of a black hole could contain an entire universe. The mathematics allows it. As you cross the event horizon and approach the singularity, space-time could branch off into an expanding region disconnected from our universe. The Big Bang of that universe would be, from our perspective, the formation of a black hole. Lee Smolin proposed a radical version of this idea: cosmological natural selection. If black holes create new universes, and if those universes inherit slightly modified physical constants from their parent universe, then universes that produce many black holes will have more offspring. Over countless generations, this process could explain why our universe's physical constants seem finely tuned to produce stars, supernovae, and black holes. We exist in a universe descended from a long line of black hole-producing universes. This hypothesis makes a testable prediction. Our universe should have physical constants optimized for maximum black hole production. Changing the constants even slightly should result in fewer black holes. Some calculations suggest this is true, though the prediction remains controversial and difficult to test rigorously. Recent calculations in quantum cosmology suggest something even stranger. Quantum mechanics permits events without causes at the Planck scale. Perhaps the Big Bang itself was such an event, a quantum fluctuation that created our entire universe. If so, the interior of black holes might be sites where similar fluctuations occur, budding off new universes in a cosmic fractal, an infinite tree of universes connected by black holes.
In the far future, so far that current timescales become meaningless, black holes will dominate the universe. Stars will burn out, galaxies will evaporate, matter will decay. Eventually, only black holes will remain, scattered through an expanding void. And then, slowly, the black holes themselves will evaporate through Hawking radiation. A solar mass black hole will take 10 to the 67 years to evaporate. A supermassive black hole like M87's will persist for 10 to the 98 years. But eventually, inevitably, they will radiate away to nothing. What remains? A cold, dark universe filled with photons redshifted to wavelengths larger than the observable universe itself. Occasional electron-positron pairs separated by distances vaster than our current cosmic horizon. This is the heat death. Maximum entropy, minimum useful energy, the end of complexity and structure. But even this might not be the end. Some calculations suggest quantum fluctuations could spontaneously create new universes in the far future. Empty space itself might be metastable, capable of decaying to a lower energy state through quantum tunneling, releasing energy to create a new Big Bang. Black holes, having played their role in the old universe, might seed new ones. The most disturbing speculation involves vacuum decay. If our universe exists in a false vacuum, a metastable energy state, then quantum tunneling could trigger a phase transition, a bubble of true vacuum expanding at light speed, destroying everything in its path and replacing our physics with something utterly different. Black holes might accelerate this process, or they might stabilize the vacuum. We don't know. What we do know is that black holes represent endpoints, places where matter concentrates, energy dissipates, and information meets its ultimate test. They are the universe's way of pushing physical laws to their breaking point, revealing the cracks in our understanding. They show us that reality is stranger, deeper, and more mysterious than our ancestors ever imagined. At the event horizon, where time stops and space tears, the universe whispers secrets about its own nature, secrets we're only beginning to decode.
There exists a place in the universe where time slows to a stop, where light, the fastest thing in the cosmos, becomes trapped forever, where all matter compresses into a point of infinite density, tearing the very fabric of space-time apart. This isn't science fiction. These are black holes. At the center of our Milky Way galaxy lurks a monster, a black hole with the mass of 4 million suns. Every 16 minutes, a star named S2 whips around this invisible giant at 5,000 kilometers per second, nearly 2% the speed of light. We've watched this star for over 20 years, mapping the choreography of its orbit to understand the gravitational abyss holding it captive. But here's what truly disturbs. Every single second, somewhere in the universe, a new black hole is born. A massive star exhausts its fuel and collapses, creating a tear in space-time. In the time it takes you to watch this documentary, approximately 3,600 new black holes will come into existence. And with each birth, physics confronts a paradox that threatens to shatter our understanding of reality itself. Today, we descend into the darkest depths of the cosmos, where the laws of nature are pushed to their absolute breaking point.
The information paradox. Hawking radiation created a crisis in theoretical physics. The radiation appears to be purely thermal, completely random, carrying no information about what fell into the black hole. If a black hole evaporates completely, what happens to all the information about every particle, every atom, every structure that crossed the event horizon? According to quantum mechanics, information cannot be destroyed. The quantum state of any system must evolve deterministically. You can scramble information, encrypt it, spread it out, but fundamentally it must be preserved. This principle underlies all of quantum theory. But Hawking's calculations suggest black holes violate this principle. Information falls in, the black hole evaporates, and the information is gone, erased from the universe permanently. This isn't just a technical problem. If information can be destroyed, then quantum mechanics is wrong at a fundamental level. If information cannot be destroyed, then either Hawking's calculation is wrong, or general relativity fails at the event horizon, or our understanding of space-time itself requires revision. Physicists have proposed numerous resolutions. Perhaps information escapes encoded in subtle correlations between early and late Hawking radiation, correlations so complex they're effectively impossible to detect but technically present. Perhaps black holes connect to other universes through wormholes, and information isn't destroyed but transferred elsewhere. The most radical proposal suggests space-time itself is emergent, constructed from quantum entanglement in ways we don't fully understand. Black holes, by creating and destroying entanglement, might reveal that space and time aren't fundamental, but arise from deeper quantum information structures. Firewall or smooth horizon? In 2012, 4 physicists at UC Santa Barbara published a paper that ignited fierce debate. They argued that preserving quantum mechanics might require abandoning general relativity's prediction of a smooth event horizon. Their reasoning? If information must be preserved, then late Hawking radiation must be quantum entangled with early Hawking radiation.
But quantum mechanics forbids a particle from being maximally entangled with two different systems simultaneously. The particle in the Hawking radiation cannot be entangled both with its partner that fell into the black hole and with previously emitted radiation. Something must give. The AMPS firewall hypothesis suggests that maintaining quantum mechanics requires the event horizon to be a region of extreme energy density, a firewall that would incinerate anything crossing it. This directly contradicts general relativity's equivalence principle, which states that freely falling observers should experience nothing special at the event horizon. The firewall would be very noticeable. It would vaporize you instantly. Other physicists strongly dispute this conclusion. Some argue the entanglement calculations contain subtle errors. Others suggest black hole complementarity, that the information is simultaneously both inside and outside the black hole, depending on the observer's reference frame, with no contradiction because no single observer can verify both perspectives. The debate continues. It represents physics at its most fundamental. Two bedrock theories, quantum mechanics and general relativity, apparently producing contradictory predictions. One or both must be incomplete. The evidence extends beyond theoretical calculations into observable signatures we might detect.
On September 14, 2015, at 09:50:45 UTC, gravitational waves from two colliding black holes swept through Earth. The Laser Interferometer Gravitational Wave Observatory detected them, ripples in space-time itself, compressing and stretching the fabric of the universe by 1 part in 10 to the 21st power. The signal lasted less than a second, but encoded in that brief chirp was complete information about an cataclysmic event. Two black holes, 36 and 29 solar masses, had spiraled together over billions of years. In their final moments, they orbited each other hundreds of times per second before merging. 3 solar masses, equivalent to the energy in 10 to the 47th power nuclear bombs, were converted to gravitational waves in a fraction of a second. The peak power output of this merger briefly exceeded the combined light output of every star in the observable universe. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Each one reveals information about black hole populations, formation mechanisms, and the properties of extreme space-time. Some mergers show surprising features. GW 1905-21 involved an 85 solar mass black hole, a mass that shouldn't exist according to stellar evolution models. Stars massive enough to produce such black holes should explode completely, leaving nothing behind. Either our models are wrong, or this black hole formed through the merger of smaller black holes. Other observations revealed black holes with surprisingly low spin. If black holes grow through accretion, steadily feeding on surrounding matter, they should spin up to near maximum rotation. The discovery of slowly rotating black holes suggests different formation pathways, perhaps direct collapse or mergers with specific orbital configurations. We began by staring into the shadow of a black hole, a photograph that captured humanity's first glimpse of an event horizon. That image represented more than astronomical achievement. It marked a moment when we confirmed that the most extreme predictions of Einstein's theory match reality, that the universe contains regions where our everyday intuitions about space and time completely fail. Through our journey, we've traced evidence from dying stars to colliding black holes, from Hawking radiation to holographic principles, from gravitational echoes to the information paradox. Each piece of evidence reveals that black holes aren't just cosmic vacuum cleaners, indiscriminately devouring matter. They're laboratories where nature tests the limits of physics, where quantum mechanics and gravity engage in battle, where the structure of reality itself becomes uncertain. We've learned that event horizons are boundaries between comprehensible physics and something beyond our current mathematics. We've seen how black holes might encode information holographically, might connect to other universes, might be the offspring and parents of cosmos. We've confronted the possibility that space-time itself emerges from quantum foundations we don't yet understand.
The current scientific consensus holds that black holes exist as general relativity describes them, that they emit Hawking radiation and slowly evaporate, and that somehow, through mechanisms still debated, information is preserved even if we can't yet calculate how. The consensus acknowledges deep mysteries remaining: the nature of singularities, the resolution of the information paradox, the quantum structure of event horizons. But certainty isn't the goal. Understanding is. Every answer spawns new questions. What is the quantum nature of spacetime? Can information truly disappear? Are we living in a holographic projection? Does the multiverse exist? Black holes remind us that the universe is not required to make sense to us. It exists according to its own laws, following mathematics that sometimes leads to conclusions that seem impossible, boundaries that seem paradoxical, futures that seem unimaginable. Yet, we persist in trying to understand. We build telescopes the size of Earth. We detect ripples in space-time from collisions billions of years ago. We propose theories of quantum gravity and test them against observation. We photograph shadows cast by regions from which light cannot escape. This is humanity's deepest gift, the ability to look at the universe's most mysterious phenomena and ask, why? To push against the boundaries of knowledge, to chase understanding to the event horizon and beyond. The universe is vast. The mysteries are endless. The journey continues.
In the far future, so far that current timescales become meaningless, black holes will dominate the universe. Stars will burn out. Galaxies will evaporate. Matter will decay. Eventually, only black holes will remain, scattered through an expanding void. And then, slowly, the black holes themselves will evaporate through Hawking radiation. A solar mass black hole will take 10 to the 67 years to evaporate. A supermassive black hole, like M87's, will persist for 10 to the 98 years. But eventually, inevitably, they will radiate away to nothing. What remains? A cold, dark universe filled with photons redshifted to wavelengths larger than the observable universe itself. Occasional electron-positron pairs separated by distances vaster than our current cosmic horizon. This is the heat death, maximum entropy, minimum useful energy, the end of complexity and structure. But even this might not be the end. Some calculations suggest quantum fluctuations could spontaneously create new universes in the far future. Empty space itself might be metastable, capable of decaying to a lower energy state through quantum tunneling, releasing energy to create a new Big Bang. Black holes, having played their role in the old universe, might seed new ones. The most disturbing speculation involves vacuum decay. If our universe exists in a false vacuum, a metastable energy state, then quantum tunneling could trigger a phase transition, a bubble of true vacuum expanding at light speed, destroying everything in its path and replacing our physics with something utterly different. Black holes might accelerate this process, or they might stabilize the vacuum. We don't know. What we do know is that black holes represent endpoints, places where matter concentrates, energy dissipates, and information meets its ultimate test. They are the universe's way of pushing physical laws to their breaking point, revealing the cracks in our understanding. They show us that reality is stranger, deeper, and more mysterious than our ancestors ever imagined. At the event horizon, where time stops and space tears, the universe whispers secrets about its own nature, secrets we're only beginning to decode.
Black holes force us to confront the question, what is space-time? In our everyday experience, space and time seem fundamental, the stage on which events unfold. But general relativity revealed they're dynamic, flexible, curved by mass and energy. Black holes take this to the extreme. At the event horizon, something remarkable happens to the concepts of space and time. The mathematical roles of space and time actually swap. Inside the horizon, the radial direction toward the singularity becomes time-like rather than space-like. Moving toward the singularity isn't a choice. It's as inevitable as moving forward in time. The future points inward. This suggests space-time isn't fundamental at all. Physicists studying quantum gravity increasingly believe that space and time emerge from something more basic. Quantum information, entanglement networks, geometric structures we don't yet understand. Black holes, with their holographic encoding of information and their violent mixing of quantum mechanics and gravity, offer clues to this deeper reality. If space-time is emergent, then asking what happens at the singularity is like asking what happens when you zoom into a digital photograph until you see individual pixels. The question assumes a continuous structure that doesn't exist at that scale. The singularity might not be a physical place at all, but rather a signpost showing where our description breaks down, where the emergent structure of space-time loses coherence.
The 2019 Event Horizon Telescope image of M87's black hole revealed more than just a shadow. The ring of light surrounding the darkness shows intricate structure, brightness variations, asymmetries, and features that encode information about the black hole's spin and the accretion flow. Scientists discovered that the photon ring, light from the accretion disk bent into a circle by extreme gravity, actually consists of multiple nested rings. Photons can orbit the black hole once, twice, even multiple times before escaping. Each additional orbit creates a thinner, fainter ring nested inside the previous one. These photon rings are like cosmic time machines. Light that orbited once left the accretion disk at one moment. Light that orbited twice left earlier and took longer to reach us. By resolving these nested rings, astronomers could theoretically watch the accretion disk's history, seeing the same matter at different moments in time. The asymmetry in brightness, the southern edge glowing brighter than the northern edge, reveals the black hole's rotation. Matter on the side rotating toward us appears brighter due to relativistic beaming. Detailed analysis determined M87's black hole rotates at approximately half the speed of light. But the most important finding was what they didn't see. General relativity makes specific, precise predictions about the size, shape, and properties of the photon ring. Any deviation would signal new physics, quantum gravity effects, modifications to general relativity, exotic matter, or alternative theories. The observations matched general relativity's predictions perfectly within the measurement uncertainties. Even at the event horizon, where gravity reaches its most extreme values in the observable universe, Einstein's century-old theory holds.
In 1974, Stephen Hawking published a paper that shocked physicists worldwide. By carefully analyzing quantum field theory near an event horizon, he discovered that black holes aren't perfectly black. They emit radiation. The mechanism is subtle and beautiful. Quantum mechanics permits particle-antiparticle pairs to spontaneously appear from vacuum fluctuations throughout space. Normally, these virtual particles annihilate each other almost instantly, but near the event horizon, something remarkable happens. If a particle pair forms right at the boundary, one particle might fall into the black hole while its partner escapes. To an outside observer, the black hole appears to emit a particle. The energy for this particle comes from the black hole's mass, meaning the black hole slowly evaporates. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is 60 billionths of a Kelvin, far colder than the cosmic microwave background radiation. Such black holes absorb more energy than they emit and actually grow. But smaller black holes are hotter. A black hole with the mass of Mount Everest would glow at room temperature. A black hole with an asteroid's mass would shine brilliantly and explode within seconds. The implications are staggering. Black holes evaporate completely given enough time. A solar mass black hole would take 10 to the 64th power years to evaporate.
vastly longer than the current age of the universe. A supermassive black hole like M87's would persist for 10 to the 100th power years. But eventually, inevitably, every black hole will radiate away to nothing, leaving only faint photons scattered across an expanding void.
In the early 1970s, astronomers detected a compact radio source at the precise center of the Milky Way. They named it Sagittarius A*, marking the galactic nucleus. But radio observations couldn't reveal what this source actually was. The breakthrough came from infrared astronomy. In the 1990s, teams led by Reinhard Genzel and Andrea Ghez began tracking individual stars orbiting the galactic center using advanced adaptive optics that compensated for atmospheric distortion. They mapped the orbits of dozens of stars circling Sagittarius A*. One star, S2, has an orbital period of just 16 years, incredibly fast for an orbit around a galactic center. By measuring S2's velocity and orbital parameters with exquisite precision, astronomers calculated the mass of the object it orbits. 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun. No known object except a black hole could contain that much mass in such a small volume. The density required exceeds anything possible for normal matter, neutron matter, or any other configuration we can imagine. In 2018, astronomers observed S2 at its closest approach to Sagittarius A*, just 120 astronomical units from the event horizon, traveling at 3% of light speed. General relativity predicts that at such speeds and in such strong gravity, the star's light should be redshifted, stretched to longer wavelengths. The observations matched Einstein's predictions exactly. S2's light showed gravitational redshift consistent with general relativity down to the measurement precision. The supermassive black hole behaved exactly as the mathematics predicted. The ubiquity problem, 1830 to 2200. As astronomers surveyed other galaxies, they discovered something remarkable. Nearly every large galaxy harbors a supermassive black hole at its center. The correlation between black hole mass and galaxy properties is striking. The black hole's mass is consistently about 0.1% of the galaxy's total stellar mass. This relationship demands explanation. Black holes and their host galaxies are gravitationally connected, but the black hole's gravitational influence extends only to the innermost regions. How does a black hole know about the galaxy's total stellar mass? The answer appears to involve feedback mechanisms. As a supermassive black hole feeds, it generates tremendous radiation and powerful jets. This energy heats surrounding gas, preventing it from cooling and forming new stars. The black hole regulates star formation across the entire galaxy through this feedback. But the correlation raises a deeper mystery. Which came first? Did galaxies form black holes, or did black holes seed galaxy formation? Observations from the James Webb Space Telescope delivered a shock. In 2023, JWST detected supermassive black holes, millions of solar masses, existing just 500 million years after the Big Bang. The universe at that epoch was too young for black holes to grow to such sizes through conventional feeding. These ancient monsters challenge our understanding of black hole formation. Either they started from unusually massive seeds, perhaps the direct collapse of massive gas clouds into black holes, or they fed at rates far exceeding theoretical limits. Neither explanation is entirely satisfactory.